Alright, hi y'all. I'm Caroline, and I'm going to be talking about the role of sonority profile and order of place of articulation in gestural overlap in Georgian. So I will lay out the main question first, then give a little bit of background on sonority, articulatory phonology, and the Georgian language, before getting into the hypotheses, methods, results, and discussion. So the core question here is, how does the sonority shape of a complex onset in Georgian relate to the overlap between those constituent consonants? So we're thinking about sonority here, and sonority is an abstract property of speech sounds that's a really robust concept for explaining phonotactic patterns and phonological properties in a wide range of languages, although there are many noted exceptions to claims made from a sonority point of view. The physical and phonetic correlates of sonority are elusive, so intensity is the most well-supported acoustic correlate. The more sonorous a given segment, the more intense it will be. This is the sonority scale that we're using, where vowels are the most sonorous, stops are the least sonorant. This is a broad scale, and it's intended to make this work as comparable cross-linguistically as possible. We're taking an articulatory phonology approach here, and in AP, the relevant unit of analysis is the gesture, not the segment, where the gesture is defined as a phonologically relevant event in the vocal tract. So an example would be the tongue tip closure at the alveolar ridge for a ta. And we're interested in how these gestures overlap in time in complex syllable onsets as a function of their sonority shape. The amount of overlap between consonants is something that's language specific and also affected by a variety of other factors within any given language. So we know that order of place of articulation affects this, front to back versus back to front. The voicing status of cluster members affects overlap, and the manner of articulation. Here, because manner is obviously very relevant for sonority, we do control for manner as much as possible within each sonority shape. An overlap and sonority have been explicitly connected before, so Chitoran 2016 proposes that the sonority hierarchy can best be understood in its relationship to articulatory timing, and illustrates this with examples from Georgian, Slovak, and Tashlik Berber, each of which have very different phonotactic patterns. Here we expand on this hypothesis by testing a wider range of onsets explicitly controlled for sonority shape, and by using multiple measures of articulatory timing. So we're interested in looking at Georgian because of Georgian's very permissive phonotactics. On the one hand, Georgian only permits vowels to serve as syllable nuclei. On the other hand, when we're looking at syllable onsets, Georgian permits basically any shape or size. So there are up to 7 consonant onsets and very minimal restriction on the combination of consonants. You can't have 3 liquids in sequence, but that's the only restriction. Presented here is the consonant inventory of Georgian. Grayed out cells represent segments that were not included in the data, largely because of sonority ambiguity. For example, the labiodental fricative va is often produced as a glide, which would introduce certain ambiguity to clusters containing that segment. So we have 2 hypotheses. The first is that the degree of overlap in sonority rises will be the least affected by order of place of articulation. So sonority rises are the most common sonority shape cross-linguistically, and we hypothesize that these could be preferred cross-linguistically because their coordination is more stable. Stable in the sense that when another variable is perturbed or changed, sonority rises will still maintain the same overlap pattern across all conditions. A secondary hypothesis is that back-to-front clusters will be less overlapped than front-to-back clusters. So previous research on Georgian and other languages has found this pattern. So we do expect to see this, as well as the general stability for sonority rises. The data here are from 3 speakers who produced target words either 8 or 7 times in a frame sentence. The first speaker was a pilot, and so the sentence for speaker 1 is Kidev Vutukvi, I said whatever again, whereas speakers 2 and 3 had the frame sentence Kalma blank Montsera, she wrote something to me. And here we analyze a total of 472 tokens. These are the test words for speaker 1. These are the test words for speaker 2, and 3, which largely contain the test words for speaker 1. The way this is organized is that cells diagonal from one another are intended to be mirror images of one another. So front to back sonority rises should be basically the reverse of back to front sonority falls, as in bregi, BR mound, and urbana, RB running. Similarly, sonority plateaus where possible are exactly flipped for order. Kinematic data were collected using an electromagnetic articulograph, AG501, and we also collected audio data using a Shure SCM262 microphone mixer at a 16 kHz sampling rate with a Sennheiser shotgun microphone positioned a foot away from the participant's mouth. For the kinematic data, sensors were attached at 3 points along the tongue, 1 at the tongue tip and 2 on the tongue body, and sensors on the upper and lower lip. We also had reference sensors on the upper and lower incisor, the bridge of the nose, and behind each ear. Participants read the stimuli off of a computer screen that was positioned 3 to 4 feet from the EMA, and all stimuli were presented in the Georgian script. Data were semi-automatically labeled using custom software. The figure on the slide here shows the relevant landmarks and what velocity criteria were used to label them, and I'll talk in detail about how each of these was used in the analysis on the next slide. So what we see here is what these labels that are abstracted on the previous slide look like when they're actually being made. So this is a zoomed in portion of the word urbana, running. The yellow bar here that I'm indicating with my cursor is the gesture for the tongue tip making ra. The black bar below it is the lip aperture for ba. The number 1 for each gesture marks the onset of the gesture as a whole. 2 marks the onset of the plateau or the target achievement. 3, the offset or the release of the target. And 4 is the offset of the entire gesture. We calculated 2 measures of overlap for each cluster. The first is relative overlap, which measures when C2 begins relative to C1's target achievement. So this distance here marked by the arrow. For this, lower values actually indicate more overlap. The lower the value, or the closer to 0, the closer the onset of C2 is to being simultaneous with C1 reaching its target. What we see here, though, would be a larger positive value. C2 begins well after C1 reaches its target. So the lip closure begins well after the tongue tip has reached the roof of the mouth for ra. The second measure is plateau overlap, which measures the degree of overlap between these plateaus, so where the constriction for the consonant is being held, basically. And here, the higher the value, the more overlap there is. So in this case, as we can see, there's actually a small lag between the 2 plateaus, and this would be represented with a negative value. We then analyzed these data in R using a linear mixed effects model for each of the 2 measures. We had as fixed effects, order of place of articulation, sonority shape, and their interaction. The interaction was not significant for relative overlap, so it was removed from that model. We also included speaker and word as random effects, and then did post hoc pairwise comparisons using EM means. And we present here p-values that are corrected for those multiple comparisons. So, relative overlap first. What we found was a significant main effect of sonority and a weaker but still significant main effect of order. All sonority shapes are significantly different from one another within each order. So front to back falls are significantly different from front to back plateaus, from front to back rises, and rises from falls again. But within each sonority shape, order does not reach significance. So to break this down by sonority shape first, let's look at sonority falls here, and we also have example clusters. So rba would be an example of a back to front sonority fall, and rga an example of a front to back sonority fall. The negative and near 0 values here show that in sonority falls, C2 begins before or near simultaneously with C1 reaching its target. So these are the most overlapped sonority shape for this measure. For plateaus, we see much less overlap in back to front clusters than in front to back clusters. This does not quite reach significance because the random effect of word here actually does a lot of heavy lifting. And then for sonority rises, the large positive values for both orders show us that sonority rises are the least overlapped in both order conditions. So that means that C2 begins well after C1 reaches its target in all cases. For plateau overlap, what we found is that the interaction between order and sonority is significant, but the main effects on their own are not. And we also found that plateaus and falls are significantly different from one another, but no other pair of sonority shapes are significantly different. So again, to break it down by sonority shape, what we see here is that back to front sonority falls are more overlapped than front to back sonority falls. And that is the opposite of what we see for the other two sonority shapes and for what we hypothesized. Plateaus, we see the expected pattern where back to front plateaus are less overlapped than those in the front to back condition. And we see the same pattern for rises, and we also see, as with relative overlap, that sonority rises are overall the most overlapped of the three sonority shapes across all conditions. So what does this mean for our hypotheses? Well, we did see that the degree of overlap in sonority rises was the least affected by order of place of articulation. So we saw for both measures of overlap that sonority rises with different orders of place of articulation were not significantly different from one another, and in fact showed the smallest difference between order conditions of any of the three sonority shapes. And this is exactly as we predicted. Why might this be the case? Well, in sonority rises, the least sonorant consonant will always be released into the more sonorant consonant. So in this case, formant transitions will not be obscured regardless of relative order of place of articulation. What about hypothesis 2, that back to front clusters will be less overlapped than front to back clusters? That one is a little more complicated. We found that back to front clusters were less overlapped for sonority plateaus, which is both what we predicted and what has been observed in previous studies. However, we saw the opposite pattern for sonority falls with regard to the plateau overlap measure. So the plateaus in the cluster Rubena are more overlapped than those in Rugeba, which is the opposite of what we predicted. So why might we see the pattern that we see in sonority plateaus? Well, most of the sonority plateaus in the data are stop-stop sequences, which require audible releases for both consonants to be maximally perceptible, so we would really only expect this to be significant in the plateau condition because that's the only place you're going to get two consonants that both need audible releases. So what can we say about the relationship between sonority and overlap overall? Well, one of the significant results here is that for the relative overlap measure, sonority falls were the most overlapped of any sonority shape. So in a sonority fall, C2 began significantly earlier relative to C1's target than for the other sonority shapes. We propose that this could be a mechanism to reduce the likelihood of an intrusive vocoid appearing between C1 and C2. We bring vocoids into the discussion here because the low plateau overlap within sonority falls and across Georgian in general creates opportunities for intrusive vocoids to appear. And in fact, these are found in both sonority rises and plateaus in other data from these speakers. But these vocoids are not found in sonority falls, which suggests that high relative overlap here works to prevent vocoids. We likely find these intrusive vocoids in rises and plateaus because vocoids improve perceptibility, and this is especially important when C1 is a stop that requires an audible release to be maximally perceptible. Sonority falls don't have this concern, and in addition, vocoids can affect the syllable parse, and we argue that sonority falls are more vulnerable to being reanalyzed as two syllables. In conclusion, we find support for the hypothesis put forward in Chitoran 2016 that sonority can best be understood articulatorily through overlap. And by using these two measures together, we can explain how Georgia maintains its unique phonotactic system. The low plateau overlap ensures the perceptibility of both cluster members, and the high relative overlap in sonority falls helps ensure a tautosyllabic parse of these potentially dispreferred onsets. Thank you.